What's up, everybody? This is Matt Brown with another IoT hacking video. Today we're taking another look at the Chinese designed and manufactured VStarcam CB73, and today we're going to look at a proprietary encryption implementation that I found this device using. If you are in the security world and you hear those words, you know that this is going to be a great day, because anytime when you hear the words proprietary and encryption put together, that's not a good thing. If you're outside of the security sphere, you might think, oh, that's a really good idea. We should have proprietary encryption because that might be more secure. It might be harder for the bad guys to figure out how it works. That is actually not true. When you're looking for an encryption algorithm that can secure your data, what you want the adjectives to be that describe that technology is more along the lines of boring, simple, old, time-tested. That's what you want. But that is not what we're going to find on this device today. So we're going to walk through the reverse engineering of the encryption that this device is implementing. And at the end, we're actually going to see data that was being sent to a server in China that contains snapshots, image data from the camera. And we're going to use our program that we'll develop along the way to completely decrypt those communications. So first, we're going to go back briefly under the microscope and review our camera here and show that we have very delicately connected up to two test pads here on the PCB of the camera. This is going to provide us access to the UART console. The TX and the RX lines are specifically what I'm connecting up to here with my two pogo pin connectors. And then on the other side, out of view, I've got a ground connection as well that I just found an easier spot to connect up to ground. And then what that is able to get us over here on our screen, we can see that we have this UART console that we're actually getting prompted for a login. In our previous video, we figured out the root password, so we could definitely log into this console if we wanted to. Today, we only need the debug logging output that we're seeing scroll by here on the screen, and that's going to be very helpful to our reverse engineering of this whole encryption protocol. So first, let's look at this encryption that we're talking about. And to do that, we're going to come over here to Wireshark. I don't know why Wireshark decided to open up the manual on me. So here we can see what Wireshark is seeing on the network. This is capturing the packets that are traveling between the device and the cloud servers in China, as well as the packets being sent between our mobile application that's running on my phone here and the device itself. So it will do local network communications, and if the phone for whatever reason is not on the local network, then it'll hit a server up in the cloud and back down to the device. So this is the UDP traffic here that I was seeing. We looked in a previous video at a bunch of different TCP-based traffic. Some of it was encrypted, some of it wasn't. The stuff that was encrypted wasn't being encrypted properly, and so we were able to perform a man-in-the-middle attack on this. But this packet data, here we can see that it's not immediately obvious that there's, text data being transmitted here, right? Because we looked here in the, the hex view, and we look here in the decoded ASCII output, and there's not any real obvious human-readable strings contained in this data here. And so it does seem like this data is being encrypted, but the question is it being encrypted in a good way that is actually going to keep our data secure when it's traversing the internet, especially when it has sensitive data like a security camera would. So what I'm going to notice here first is that we see kind of this this protocol taking place. By the way, the IP address ending in .65, that is my mobile phone, and the IP address ending in .21 is my device. That's just what DHCP handed out to these two devices. And so what you'll see first is that this request being sent, these 4 bytes being sent from the phone to the camera, and then some of this is out of order here, and then the camera will eventually respond with a message that looks like this, or like this. Either way, it will respond with some number of bytes, and then my phone will say, okay, yeah, I see those bytes. It will respond with the same number of bytes, and then when we actually do things, we actually start to perform actions inside the mobile app, that's when the interesting data starts coming along that has the longer length. So here we can see a bunch of packets with the length of 24. So there are 24 UDP, inside the UDP payload, there are 24 bytes in this packet. And again, don't see any human readable text contained in here. And so we keep scrolling along, we have some more packets, and then we get to a packet like this that's a little bit longer in length. And so we're interested in, you know, what could this correspond to? Well, this is where that UART console is going to come in handy. So what we're going to do is I'm going to generate this data again. I'm going to clear Wireshark. We're going to go into our phone app here, and I'm going to click into the app, and we're going to make sure we have a live stream to my device here. And so we're going to see, yeah, you're going to see all this data streaming by. We can even look at the beginning of these communications here, and we see that same thing. We see some length of 24 and 40. Oh yeah, so here this is a great example. So here we see some of this data going to a not local IP. So all these IP addresses here are those Chinese servers. But we also see some peer-to-peer communications. Let me just scroll down and find my key packet again here. That is a known length that I know here. It's 145 bytes. And so what we notice over here on our console is that when that happened, we saw all of these very interesting logs occur that say things like, you know, okay, so here we see that it has, it's talking about something, referring to it as a P2P push socket. We see the phrase P2P, peer-to-peer, referred to a lot in these debug logs. So that's going to be a really good hint for us to go look for something related to P2P encryption later when we start doing more reverse engineering. But we can see here that it's decoding some kind of a command. And so it actually looks like HTTP, but this is coming from that UDP traffic. What we can do if we really like watch what we're doing in the app and what we see over the network, it correlates. It's not correlated to any kind of TCP-based traffic. It's correlated to that UDP traffic when these log messages appear in UART. And so we can deduce that this message right here, because this is the first message that kind of appears for some time, actually relates to this packet in Wireshark. And so what I was able to do is that over time, let's actually take this, the actual data, all of the data, and we can apply a filter. And so what this is going to do is it's only going to select packets that have this exact payload, byte for byte. So if you're using a good encryption technology, let's say you were using TLS, even if you were sending the same data over and over again, like the unencrypted data, when it gets encrypted, it should change every time, right? But if we select this, we can see that there are, you know, multiple packets that are getting sent with the same exact UDP payload. And so that is an immediate red flag, and it leads us to want to conduct our first attack, and that is a replay attack, where we simply take this data and we try to send it out over the wire again. And so that's what we're going to do with a quick script here. So I already recognize the contents of this data, and we are going to get our script that is already ready to go. I'm going to just click down in our console. So what I have here is my simple replay Python script. By the way, all these scripts are going to be available on GitHub, including some of the binaries that I'm reverse engineering, so you can follow along at home with all of this. And so what I've deduced, and this took a little bit of time looking through the Wireshark packets, is that there is actually an initial handshake that occurs. So you have to send this 4-byte packet out, and then you have to receive a packet back. So I'm receiving that into this data variable, and then you actually have to send the exact data back to the server side if you're pretending to be the mobile application, which is what we're trying to do here. We're trying to talk to the camera as if we're the mobile application. And then we're going to send the packet. So after we do that whole handshake thing, we're actually going to send our request, which is this bit of hexadecimal, binary data, and it's going to encode it into binary and send it along. So let's just quit out of that, and let's run our script. And let's make sure I'm right up to date here. And so we can see that it actually, right when I sent that request, it received that get status command, which proves that we have successfully conducted a replay attack, right? We took that data off the wire. It's encrypted. We can't see what's inside it yet, but we can trick the device into decrypting and processing that data, because there's no replay attack protections. There's no message ID that's incrementing that might prevent this style of attack. So we can use this to actually find out even more about how this encryption protocol is working. And this was actually, what I'm about to show you was my breakthrough, because we're going to then jump into reverse engineering the binary in Ghidra, where I really hit a wall. But because I had the information that I found right here, I was able to overcome the wall I was hitting in my binary reverse engineering. So let's look at this simple replay again, and let's just try to modify a few of the bytes at the end of this packet. So let's take, like, I don't know, let's just take 5 bytes off. 1, 2, 3, 4, 5, and let's replace them with all A's. Okay, and then we'll save and write that file out, and then we will run our replay attack again. Let's just clear our console. So now, if we look at the command that's parsed, we can see that it's all ends at the end. And another interesting thing to note is that we changed 5 bytes, but we only see 4 ends. So that is going to be really relevant to how we understand this protocol and reverse engineer it, because there's a real trick that threw me for a loop for a long time, but I finally pieced it together. So here we're able to actually get back. We're able to send it encrypted data, and then it will decrypt our encrypted values that we don't even know what they are when we're throwing those A's, those AA bytes. Like, we don't know what that's going to turn into on the other side. But here, because we have access to this UART console and these logs, it's actually, we're convincing it to decrypt the data for us. So in cryptography, this is actually referred to as a chosen ciphertext attack, where you are able to provide a ciphertext, an encrypted message, and then convince some system to then decrypt it for you, and you're somehow able to observe the decrypted result. And you can use the information that you gain by that decryption to get at encrypting other messages. Obviously, if you have some way to access those specific decrypted messages, well, then you can see inside of them. But if you could use that information that you find to conduct a set of tests, a set of experiments that allow you to then decrypt a brand new message that you've never seen before, that you maybe will never get the output of, that would be an interesting attack. So that's what we're going to do here. So Let's now go over to Ghidra, which I believe I have in this window. So I've cleared all of my reverse engineering, saved progress here. So we're gonna start from scratch. We're gonna say, yes, we would like to analyze this binary. Let me get this all in one window for us. So it's not gonna take too long for it to reanalyze. If you've seen my previous video about reverse engineering the root password, this same binary, this binary is basically the one-stop shop for doing everything on this system. It, configures the root password, it configures the Wi-Fi, it, encodes data. I assume that was probably the first thing that they made it do. And it also is responsible for doing this peer-to-peer communication between the mobile app and the device. And so what we're going to do is we're just going to search for, kind of using like encryption or decryption, right? So let's just put the word crypt, because then we're going to get both sides of it. So over here in the symbol tree, these functions are listed. So we're going to get to see what kind of functions, named functions, exist inside of this binary. And we immediately see something that is a huge red flag if you're in the security world. Like we talked about at the beginning of this video about proprietary encryption and how bad that is. Here we see the encryption functions inside this binary are actually named, P2P, peer-to-peer. So there's that reference to what we're seeing in UART. So we know this is probably a good function to reverse engineer and hone in on. So we have P2P, proprietary, decrypt, and encrypt. Well, let's go ahead and look at this proprietary decrypt function, and we're going to move our Ghidra window over a little bit, and let's increase our font size there. So what we have in this function, I'm not going to go over every part of my reverse engineering experience with it, and I probably spent a week banging my head against the wall inside of this function, and honestly, answer me in the comments if you figure out the thing that I couldn't figure out the whole time. So what I did figure out is that, so it obviously takes in these 4 parameters, right? Parameter 2 here, this is kind of like the input buffer, right? So this is our encrypted buffer. Yeah, that's not even spelled right. You know what, that's okay. And then decrypted buffer, and then we're going to rename this variable, and this is just a size value. So this is the size of, it's the size of either the encrypted, both the encrypted and the decrypted buffer, because they are the same. This is a stream cipher that is being conducted here. We can see that is obviously the case. Based on us changing that data and seeing in UART that it's like changing kind of 1 byte at a time instead of big blocks, like a block cipher would do, larger chunks of bytes. It would change all at the same time when you change one piece of input data. Yeah, it's clearly a stream cipher. So we have this section right here. If you can explain to me what is going on here and how it is relevant to the rest of the code, I am posting all of this stuff on GitHub. It'll be in the link in the description. Please comment or come to our Discord server and let me know what I missed. But the long story short is I don't know what's going on here. I do know that there's this variable that gets kind of generated here that I'm going to refer to as a seed. And we're going to talk about why I call that seed, because that gets sent as an input to this function. Okay, we're going to rename this because my ADD is going to mess with me. Encrypted, buffer. So this function, P2P, proprietary select table element. Again, the proprietary thing, they're just like bragging that this is, this is great. This is proprietary, awesome, super secret encryption. I can see it right here. It's not that secret. All right. And so this takes in that seed. We'll name these parameters just to make sense. And then this is the, okay, we're going to call this, oh wait, what is this? Oh yeah, this is like our encrypted Oh yeah, oh yeah, oh yeah. Okay, so this is actually what I'm going to call previous. So this is our previous byte, and why I say that is because here we can see that it passes in encrypted buffer -1. So it is grabbing the byte before the current byte that's attempting to be decrypted, and it's passing it into this function. And then what it does here is this is our, this is kind of like our key. It's going to get our key out of here, and then what it's going to do is it's going to take that key byte and it's going to XOR it with our, encrypted byte, right? Just like that. So this table, what we can do is we can actually go and double click on this table that it's clearly just, taking the seed and the previous byte that the previous encrypted byte before it got decrypted, and it's just mixing it and it's grabbing a value out of this table. Well, what's in this table? It's a table that has 256 values, right? So that's how many values there are within one byte, and so we have this lookup table that has just different byte values. It has a whole array of byte values there. So what I was actually able to do, this is a helpful hint in Ghidra. You can just right click, go copy special, and you can create a Python byte string. And this is actually how I generated the Python code that we're going to talk about in a minute that does all of the decryption for this protocol. So let's go back. So that's where I got the actual data inside of this table, is from there. Let me go back, and let me pull the decompilation window back over so that we can see that. Okay, so what we want to do is we want to know what seed values correspond to these encrypted, the previously encrypted byte, right? So what I don't understand, and this would be helpful if somebody else knows, like this seed, if we highlight this, this variable, let's highlight it. We see that it gets updated here in this top section, but then when we're actually doing the decryption, it passes a reference to it into this function, but it's not actually changing the value of the seed inside of here. So I would think that it would stay the same all the time. And maybe that is true, but what I'm going to show is how I was able to use the knowledge of I have an encrypted packet, right? And I have the decrypted raw data. So because of the way XOR works, if I know what the seed, if I don't know what the seed is, but I want to figure out what these seed values are for each and every byte, I can just kind of do the calculation in reverse. So to explain that better, I'm going to show you the Python script that implements some of this functionality to decrypt our data. So let's go back over here and let's go to generate byte seeds. We'll just go to V1. Okay, so these first two functions, let's make our screen a little bit bigger for now. So these first two functions, all they do is when it figures out these seed values, which we're going to talk more about in a little bit here, is it's going to save it so that we can use it later for our decryption process. Here is that table. So this table variable is exported from Ghidra, right? That copy special, copy it as a Python byte array, bam, right here. Now I have this get lookup function. And so this will look very familiar because this code right here, go back to Ghidra, is the same thing as this right here. It's just taking the seed and the previous value, and it's computing the correct value to pull out of the table. And then back to our code. So that's just this get lookup helper function that I've described here that has the seed and the previous value. But what I really found out is that the seed and the previous value, they really are linked. So I kind of don't know why it feeds in both of them. And then I've got a list here. So right now there's only one thing in it. So here we have that clear text data that we pulled out of UART. So that's our target, or what we want it to decrypt to. And then we have our encrypted data. So this encrypted data is not is longer than this target text because the protocol has, I think it has about 16 bytes of a header in front of it. So what I do here is I have it like strip off. I basically have it take the length of the target, and then it only looks at the last, X number of bytes based on how long the target is. And then it's going to attempt to use that data to effectively brute force what the seed at each byte value should be, because there's only 256 options for what that seed variable could be, right? So let's just go back to Ghidra and talk about this. So I'm really confused at how this value right here gets generated in that other function. But since it is getting cast here, or it's getting XORed with byte FF. That's the same thing as taking it mod 256. There's only 256 possibilities, and so I can brute force it. And so that's what we're doing with this code. We start the seed at 0, and so for each byte, I basically attempt to, each encrypted byte, I attempt to decrypt it with every possible seed, and then I check which one decrypts to the target value. Right? So a good example is, here, if this is the byte right here, so this O2 is going to decrypt to this ampersand. And it also needs to know the previous encrypted byte, right? Because that's going to feed into the formula. But I'm going to keep guessing all of the seeds that are associated with the 60 byte, because it's this previous byte that actually determines what the seed is. And so we're just going to loop through every possible seed, and then once we find that the decrypt, so this is our decryption process right here, this XOR cipher. So it's going to get the element from that lookup table based on our guessed seed, and then it's going to XOR it with the data, and then it's going to get its decrypted, its like candidate decrypted value. And then we're going to say, okay, does that decrypted value equal what we expected it to be? If it is, then what we do is we add the seed to this database, and then we build up a database of all these seeds. And I just need to find one byte for every byte from 00 to FF, and then I'll be able to decrypt any data I want. So let's show practically how this script works. So first, I'm going to make sure, okay, so I've already blown away my seed database here, so I'm not going to be cheating here. We're going to run this code, and it goes through that encrypted message, and in that encrypted message, it finds 99 unique bytes and then calculates their seeds. So now in this database, I can say print seeds. It's got, all these seeds, which interestingly, there's only 4 values that ever occur for those seeds. There's, 210, 95, 4, and 45. And in the end, the fun thing about it is they're all evenly distributed. There's only 64. There's 64 of each of them. There's probably some reason for that. I don't know. But so now we've generated those seeds. Now let's go and try to decrypt a completely different piece of data. So let's go back to Wireshark. Let me go back to my previous filter. Yeah, this is probably a good filter. Wait for it to load because there's a bunch of packets here. Okay, perfect. Let's pick this packet because that looks interesting. So I'm just going to copy hex stream. And then I'm going to go back here. So I have this decryption tool, which uses a lot of the same functionality, so we can skip past most of it. The same git lookup function, everything. It's going to do the same exact XOR cipher, except this time it just is going to, keep track of all the bytes as they get decrypted, and we don't have to guess the seed. And because we're either going to get the seed from the database, or if the seed is not in the database, then what we're going to do is we're just going to have it be an underscore. So when we see an underscore, we won't actually know if it's like a properly decrypted underscore or if it's just like it couldn't decrypt that byte. But it shouldn't be too big of a problem. So we're going to feed in our data to our decrypt function, and we can see that it's piecing together byte by byte. It is starting to decrypt the data. Now, we don't have all 256 values yet, but you can see here, this is clearly going to say log on or log in, and here's part of that password that we saw before, right? This is clearly text-based data that looks like that other data we saw. So to skip ahead, we have this other function that no, not the V1. So in this upgraded version of this program that's going to generate all these seeds, I just have more targets here of the clear text that I saw on the UART console, and I was able to use some guessing and checking to correlate it to what the encrypted message was that was sent by the mobile app up to the device. And so I have a bunch of these, and so now when I run this new generate byte seeds, it's going to go through there and it's going to find all 256 seeds. So now if I run this same decryption program, the one that before, when we only had like 99 seeds, it was only able to decrypt some of the data. Now we can decrypt all of the data. And you see some binary data up there at the top. That's because if we actually look at this protocol, we will actually see that it has this concept of a header. It has like a 16-byte header, and then it has some amount of data, and then it will actually show, I believe this is actually a length field. So when the header gets decrypted, so this is saying that after this point, that 63, convert hex to int, that is how long this next sub-message of the protocol is. So pretty cool stuff. So now we're able to decrypt all these messages that are occurring from my mobile phone to the device. But I mentioned that there's also data that is going directly from the camera up to cloud servers in China. And so I'm going to show you a PCAP that I gathered. And so this is a filtered down PCAP, so it only shows the bytes that I care about right here. And so we can see large chunks of data. And just based on my experimentation, this protocol has a maximum UDP payload size. This proprietary protocol has a maximum size of 1,032 bytes. That's its max size. And then if it needs to send data longer than that, it will chunk it into multiple packets. And that's what we see here. So all I did was, you can go here and you can go follow the UDP stream, use the word stream loosely when we're talking about UDP. And so I just copied all of this data into a Python script and then used all those same decryption utilities. So let's look at my image decrypt. So, yep, we see the same exact functions here, the same table. We're going to see big chunks of hex data in bytes. So data 3, 4, 5, 6, 7. So those are all these packets. I'm just going to pack all of that data into a list, and then I'm going to loop through it, do the same decryption that we did before. Otherwise I print the underscore, but I'm never gonna have a seed that I have all the seeds, so it's never gonna hit this else block again. And then when the image data gets decrypted, I'm taking off the first 16 bytes in each packet because that is that header that we saw. So we have to remove that. And then I'm going to actually write it directly to standard out in my code here. So if we do this all correctly, we're going to say, you know, snapshot.jpg. And then if we run the file command on this, we're going to see that it actually recognizes it as a JPEG file. And then I'm going to go over here where I can show a full screen view of this image. And here we go. I'll zoom in on it. So obviously, I have some alignment issues here with this snapshot data. I might have been removing too much data, or I might not be removing enough data, but you can clearly see down there at the bottom, that is the date, the little overlay from the snapshot that it took from my device. It's pretty black because, as you see, I definitely don't trust this Chinese device, and I've the entire time I've been doing all this research, I have the shell of the camera sitting right in front of the camera, so I can't actually see anything in my office here. So that is, again, this data, if we go back and look at that PCAP, we see that this is a public IP. This is not local communications. This data is being sent to a cloud server in China with this inferior encryption technology that can be easily decrypted if you are able to capture the traffic. So thank you for watching this video. I hope you enjoyed it. Please give me a subscription, drop a comment down there, and tell me what you think about this video. Also, hop in our Discord channel, especially if you are really good at Ghidra and you want to help reverse engineer this program some more. I would really love your help. Thanks and have a good day.